Okay, the other day, that is exactly on 2nd February, we have discussed this problem, which is a case of a truss solved by flexibility method, matrix method. In this truss, we have uh, an active force, 10 kilonewton acting, support settlement was there, then temperature in AB, one of the member temperature is also increasing. That is one active force and two pre-strain cases. Okay. So this problem, you can see the global coordinate, how we have solved this using what global coordinate. We have selected one as the global coordinate for capital R, that is 10 kilonewton. See, let me tell you one thing. If you are okay with our notations, capital R, small r, capital Q, small q, capital X, small x, then only you can understand what I am going to discuss further. So if you are not clear on all those notations, then please pause the video and try to understand the meaning of that, then restart this video. Okay, otherwise it will be very difficult. So discussing or continuing, so 10 kilonewton is in coordinate 1 for capital R. Then we know that ds is 2, one internal, one external. So we released that member AC and coordinate 2, which is representing x1, that is redundant 1. Then we have removed the support at C, uh, because that is an external redundancy. We have removed that, and that is coordinate 3 representing x2. So we have one r, one x, two x's. So one r, x1 and x2 in this problem. This we have already done. Okay, now I increase the complexity of this problem. That is, by this solution, you must have noted that the support settlement at C was directly C is the top support. Okay, that is directly coming into coordinate 3, global coordinate 3. Or otherwise, that support settlement at C 10 millimeter, we have taken that quantity directly into x2, small x2. Small x is the displacement. Small x1, small x2 in that, because we have capital X1, capital X2, we have small x1, small x2, and that 10 was directly taken into small x2, and we have proceeded with the inversing, etc. That is a solution process which is given by capital X equal to minus fxx inverse, okay, into x into x plus fxr r, that equation, or capital X equal to fxx inverse multiplied by x minus fxr r. So there in that small x, we have directly taken this point, sorry, 10 mm. But now the complexity is increasing. That is, I am adding one more support settlement at D. Okay. So what will happen if the support settlement at D is also included in the problem? You cannot take that D directly into either small x1 or small x2, because those coordinates are not there. Coordinate 2 and coordinate 3 are not along support D. So the issue now becomes that settlement of D can only be taken in some coordinate other than small x. So what is available for that? Coordinate other than small x are either small q or small r. Okay. So this discussion I am repeating will be clear only if you know the meaning of small q, capital Q, etc., etc. Okay. So remaining is small q and small r, and we have seen small q is utilized which are the member displacements, are utilized for including temperature effect, because in this problem we have temperature effect that already you have done that also. So small q is only useful for either temperature or lack of it in process. Okay, now what is remaining is small r. So how this small r is to be utilized in the analysis, that is what our additional complexity, or that is what I would like to discuss today. So this problem, if you study this problem, all the issue related to uh, flexibility method, Truss solution, all the type of loading, that is temperature, active loading, or this type of support settlement in whether in small x or small r, everything can be or can be solved. Or so every issue related to a Truss problem is addressed in by flexibility method in this discussion. Okay, so be very careful if you need to understand this. Then, as I told you, you should be very clear on what we are discussing about the symbols and all. Okay, so I have modified that problem. You must be reading that here. Same truss, A, B, C, D, no change. All the quantity AE is 20,000, alpha is 1.17. So these quantities we have already evaluated. That is L alpha T for temperature. Though, so I may not be repeating that. I think we got minus or 0.351 millimeter as the expansion due to temperature. So that is retained in the problem. AB, member AB increases, temperature increases by 10 degree, that is retained. Then support C is settling to right by 10 mm, same thing of previous problem. And what is added here is support D settles down, okay, down by 5 mm. I think you know the importance of support settlement in structural analysis and design, etc. So I am skipping, I have already discussed that. So here, our complexity is increased by one more item, that is support D settles down by 5 mm. And let us see how we solve this. Okay, so in order to solve this, I'll be using the same coordinates, etc., global and local coordinates. You can, as you can see, as you can see, the same thing, nothing new. Previous problem, we have coordinate 1 for representing the 10 kilonewton, that is for capital R. Then 2 for representing redundant member, internal redundancy AC. Then 3 for representing that redundant support C. I have selected support C as the redundant. And also that formulation. You can try same thing with C. Instead of C, you can try taking D as the support and removing D. Anyway, that you can try. We are not discussing that. We are only removing C here. So global coordinate 1, 2, 3. Now local coordinate 1 star, 2 star, 3 star, 4 star, 5 star, 6 star in the right side diagram. Please note that whenever you notate global coordinate, the truss or whatever be the structure should be primary or statically determinate. And when you number the local coordinate, all the members should be available. It is okay up to 6, because you can just compare. In global, we have removed that 6 star, but in local 6 star will be there. These are all related to the initial principles or whatever we have discussed. Now, what happened here is one thing is missing, because how to model that settling 5 mm of D, that is what is missing by us here. So we need to think of how to do this, and we have seen that out of, you cannot take that, this can be taken in x, that is exactly in x2 you can take it in the solution, but this 5 mm cannot be taken in x. So remaining are q and small r displacements. So q is good for temperature or lack of it. So this we can take it inside this. Now what is left is only small r. So how to consider this small r, how to include, that is our basic discussion here. So first thing, you know that you need a small r here. That is, you need to as you can page down, page. You can see I have added a coordinate here. What is the reason? The reason is quite general. See, all selection of local coordinate, global coordinate. That is, in fact, even though it is different or specific to each given problem, the principle behind that is one and same. So once you study the principle of marking global and local coordinate for one problem, you can apply the same principles to other problems. So you should study like that, not local and global coordinate of one problem, study that separately, by heart global coordinate of some other problem separately, then a third problem, study that separately and by heart. Don't do that. Just by heart the principle. If you do that, if you know the principle, you can blindly any new problem, whatever you have not been exposed to, you can mark the local and global coordinates. So that should be the approach. Or that should pain you should, that much pain should you take. Then only you can attack any problem, whether it is in flexibility or in stiffness. That is marking global and local coordinate. So here, what is the principle in marking R2 here? There is nothing. I need a small R2 to represent this, isn't it? That is our requirement. For representing this, you cannot use small x, you cannot use small q, you can use only small r, and capital R1 is already reserved for that 10 kilonewton in our formulation. So you need a capital R2, or in small r2 you can represent this 5 mm. That is a general principle. Okay, now that means suppose this problem changes to support A, settles down by 5 mm. Naturally, that R2 has to be marked at support A, not at support D. So why we have marked R2 at support D is settling down. Okay, so that general principle I have applied, and finally this is the set of coordinates. So you can see that uh, x1, x2, x1 and x2. X1 should be marked in a double manner because you are changing a removing a member. So x1 should be marked like this. Anyway, the name is only one coordinate, one. I have selected one as the coordinate number. The next two is the support. So two there. Then R1 for the 10 kilonewton, R2 for the 5 mm down settlement. So I have marked that as coordinate 3 and coordinate 4. So we have 1, 2, 3, 4 global coordinates in this problem. Okay. So one is that redundant member, two is the redundant support, three is the 10 kilonewton applied force, four is the support settlement of D. Now, what about support settlement of C? You can take it in small x2. What about temperature 10 degree? That you can take it in small q. So everything, every arrangement is made to accept those initial or whatever loading. So that is also general principle. There is nothing new or specific to this problem. Now, once you do that, once you mark the global coordinate, then almost your problem is just mechanical. There is nothing, you can simply do it. Now, so for that you need Bx and Br to start with. So Bx apply successively unit force at coordinate 1 and 2. So this diagram is for the column 1 of Bx, like that is unit force is applied on that removed member, or instead of the removed member I have applied 1 there. So this one is for column 2 of Bx. I have applied a unit load at coordinate number 2. And this one is for column 1 of Br, or coordinate 3, whatever you call it as. Unit load here, that is by removing coordinate 3, or instead of coordinate 3 I have applied a unit load. Then this is for fourth column or column second of Br, that is coordinate 4. a unit load is applied here. Now, once you apply that, you analyze or do the truss analysis of first one, you get the first column. Do the truss analysis of second one, you get the second column. Then do this truss analysis, you get this column. Do this truss analysis, you get this column as usual. Here also, nothing new is there. So BR and BX we have evaluated. I am skipping how to calculate all those things, etc. Okay, I think that you can do. Just truss analysis on a determinate truss. Now you need fx, that is unassembled elementary matrix. That's a single diagonal matrix. You know that 3 4 3 4 5 5. That is 1 star, 2 star, 3 star, 4 star, 5 star, 6 star. That is L by AE. You know, AE, we are just all elements AE same. So AE has been 1 by AE has been taken outside. L is kept inside. So length of first element is 3 meters. Second is 4 meter. Third is 3, fourth is 4, 5 is 5, 6 is 5. Okay. Then we have to think a little bit about handling small r2. So this 10 kilonewton, this direct, you know, it is to be taken in capital R. Okay, here R1, R2. So R1 is minus 10, R2 is 0 because there is no applied force at support D external force. Okay, only that 3 coordinate 3, it is in the reverse direction, that's why minus 10. Now this R2, that is going to be indirect. So for that we need to make a this one, because that is not available in x1 or x2 as it is. We cannot take it in x1 and x2, so we need to go it for a indirect method. So that discussion we are using is superposition. I have explained about this when I was describing the first problem. I have explained you where if that support settlement is not coming in small x, you need to go for some superpose method, etc. It's not straightforward. All these things I have told you. Okay, so we need to go for a superposition. So how will you superpose is, assume the structure is determinate. That is, remove that member AC and support C as just now we have done in the global coordinate system. Okay, so that is that is determinate now. Okay, so when that is determinate, this equation, I'm repeating the equation. I will rewrite the equation here. That is, you know the basic equation of flexibility, Rx is equal to FRR, FRX, FXR, FX. You know this equation multiplied by R and X. So when we assume the structure to be determinate as in the global coordinate we have selected, what will happen is no, no redundance. So no x, because x are redundant. You can, this is nil there. So when there is no x, what happens is actually actually that can be taken as all zeros. We are here we have x1, x2. Okay, so this small x, everything will go when you have a redundant determinate system. That is the discussion. When you have a determinate truss, capital X will not be available because capital X is redundant. So that is what I have written here. Same thing I have written here. Okay. Now, with that assumption, you can write the equation. Same thing here. Just written the modified form. So with that, you can write an expression for small r. Okay. Just matrix manipulation. So small r becomes FRR into R. isn't it? Because if you multiply that in this fashion, that multiplication, will give you small r is equal to f r r into r, because capital X is absent because determinate. And also you get even though capital X is absent, small x, for example, you see in this diagram, okay, capital X1, capital X2 is absent in this, that is coordinate 1 and coordinate 2, there is no restraints. That is in coordinate 1, there is no member. Coordinate, you see this diagram. Coordinate 1, there is no member. Coordinate 2, there is no support. So due to that, small x1 and small x2 will happen because nothing is restrained. Of course, support is not there at C, so it can move towards that. So that small x is taken as x initial, which can be evaluated from capital R. Okay, this is the flow. And this capital R can be evaluated from this small r by inverting this equation. So I will rewrite the same thing once again here, then you will understand. That is this from this equation I write x equal to f xr into r. This I will modify f xr into what is r actually. That is from this set of equation I will get capital R as f r inverse, that is from this equation I get f r inverse small r. So what happened here is by this equation you have converted small r, here exactly small r2, into that x in, okay, small x, so x in you have converted that, okay. So that is what is to be done in order to handle small x to sorry, small r to. I hope you got it. Now, even though you will be getting an x in by this expression fxr into frr inverse into small r, but when applying the solution you have to be a little bit careful because we have assumed the structure to be determinate to get this equation. Now we need to reverse the effect, then only your structure will be in original position. That is especially how to reverse the effect. You have to arrest coordinate 2 in x in e. That meaning in x in e you will be getting some numbers, some point 1, point 2 you will be getting. Okay. So to reverse it, first of all you have to arrest it because this is coordinate 1, coordinate 2. Coordinate 2 is a support, so you have to arrest it and make it 0. Then only your structure will spring back to the non-determinate one or indeterminate one. And also since you are applied this one 0.10, you reverse this and point minus 0.10 has to be applied. Okay, this is a very, actually you may think that why we are arbitrary doing that. We are not arbitrary doing it. We can derive this, even though I have discussed the reason, etc. But in a more elegant, rigorous manner, we can derive it. That we are skipping. I have just explained the principle. That is, once you got x in e, that x in e was on a determinate structure. Now you need to take back the structure to indeterminate one. So for that, support, for example, here support C has to be arrested. So make the value to 0 for that. That is coordinate 2. Value x in coordinate, value in coordinate 2 has to be cut to 0. 1 has to be uh, modified to the minus sign, reverse sign. Okay, so that is a principle. So now with that we can start doing the problem fully. So as usual you got BRBX. Now what you need is FXR, FRR, FRX, FXX, etc. Out of this FRX is of no use because that is just the mirroring major transpose of FXR. So, and that will not come into our equation process. Only three metrics will come into this: fxr, frr, fxx. We have seen the equation also. Or otherwise, newly frr is coming into our formula. So far, we have not anywhere, we have not a frr. So the change in solution methodology, when you have a small r2 or whatever, is that bringing up of frr into the solution. So we have evaluated everything. Now, as I told you, first let us calculate the XINI due to the settlement of R. Okay, so this is the settlement in coordinate 3 and coordinate 4. Coordinate 3 is the location at B where the 10 kilonewton force is acting. There is no initial displacement or prescribed displacement there. There is only a force. So small r1 is 0. This is 0. Small r2, there is a prescribed displacement or support settlement in the reverse direction, because our coordinate 4 is here. This coordinate 4, you can see that is upward, but settlement is downward. So minus 0.05 is taken. So sign convention is also straightforward, nothing. So minus 0.005. Now we apply this equation. That is x initial equal to fxr into this is fxr. Okay, this is fxr. And FRR inverse, this is FRR inverse of this multiplied by this R, that is R is 0 and minus 0.005. So three products, three items you need to multiply. As a result, you get this result 0.003 and minus 0.004. That is the XINI. Please note that is the XINI. We got on what? We got on a determinate structure. Now in the solution, we push it back, original, back to original. So in original, you have two arrested, isn't it? Two arrested because two is a support or support C. So you cut this to 0, make this to 0. And this one is a consequence of releasing that member AC. So apply this in the reverse direction for presence of AC. Okay. So this vector is modified to this vector. You can see we have synthetically removed the second coordinate value to 0, and the first coordinate value is reversed, minus sign. Okay, I told you the reason for that. I'm repeating. In coordinate 2 you have a support C. In coordinate 1 you have removed the member AC. Now you need to refix the member AC, so that value 0.003 has to be reversed. And coordinate 2, since you are support, you have made it to 0. Very simple principle, nothing is there. And I am repeating, we can derive this from the fundamentals. Okay. Now, the next XINI. So one XINI due to R2 we have taken care of. Next is XINI due to temperature. This already we have done, so I need not to explain you all these things. In last problem, we have attacked this. XINI due to temperature is available in small q. You know how to change that small q to x by using the equation x is equal to bx transpose small q. This equation, we have applied into the 2nd February problem. That is the previous problem. Bx transpose into small q. So bx transpose is bx is already available. So transpose I have written here. Small q I have written here. Small q, the member temperature is changing in one star. Okay, only in one star. All others there is no temperature. So one star is temperature is increasing by 10 degree. Here it is given. AB's temperature, AB is one star, increases by, so it is too long. So in order to fix it back, or due to the temperature, what happens is that member will apply compression. So compression is negative. That's why we have taken a minus 0.351 here, as same as in the previous problem. So here uh, we have obtained 1 and 2 coordinate 1 and 2. See here in this formulation, please note that we have not assumed the, see, that is I'm comparing with the previous one, r small r2 case. Small r2 case in the formulation, we have taken x is equal to fx is xr into r and x, and in that case we have cut this and then formulated, and due to that xini had to be adjusted. But here in this case, we have directly taken the property of structure, that is Bx transpose Q equation. We have nothing manipulated, the structure has not been manipulated. All the six members are coming in this particular equation. Bx transpose also all the six members. Okay, so nothing we have removed. So no need to modify this. So keep it as it is in the solution. No zero or negative sign, etc. As in the case of previous x in due to support settlement in small r. So in small r, that is in the previous slide, we have modified x in E. Here there is no need of any modification. You can directly take it. So here no modification. You take this directly into the solution. Okay. Now next is okay x in E. Okay. One more thing is there. Yes. What is the next initial condition? Yeah, of course, this 10 mm settlement. That 10 mm settlement, that is in support C, and you know that at support C corresponding we have a second coordinate x2. So this can be directly taken in small x2. So that can be directly available. That is available in the solution equation. Solution equation is, you remember, capital X equal to f x inverse. We have already derived this, and we know here one x is there, minus f xrr, that one x how it came. Okay, now we are splitting it into three x initials. Okay, so that I will be doing now. That is x initial x ini due to settlement. This settlement is in x, small x. Be very careful. ഇത് മനസ്സിലാക്കിയെടുക്കാൻ ചെറിയൊരു ബുദ്ധിമുട്ടുണ്ടാവും. Okay, xini due to settlement in x. Example here is that 10 mm settlement of support C plus x I am adding xini due to temperature. This how we took q, we converted to x by bx transpose q plus xini due to again settlement, but this is in small r, in small r. So this how we have taken that small r was converted to x by fxr frr inverse into small r, like this. Okay, so this much three things we have done here. So that is a recap also whatever you have done. Minus fxr into r. This r that is minus 10 and 0 in this particular formulation, coordinate 3 and 4. Okay, so this is the whole thing. So x in all three quantities. Okay, this is original in x, that is the 10 mm settlement of support C. This is what we got earlier due to temperature. This is what our modified x in due to small r2. Okay, modified, but this is made 0 and the sign is reversed. This much we have here, etc. No sign reversal here, only that is required. Okay, reason also I have explained it. Now I have taken everything from Excel. Same thing, x equal to, this is f xx inverse. Okay, I have directly taken the inverse, and that was in fxx we had 1 by ae, so ae will come up. This ae has to be substituted as this value 20,000, because otherwise, because you have mix up of quantities. These are in meter. Okay, here this is 1 by ae, so its unit should come into this. So here as well as here 1 by ae, this is 1 by 20,000. This was 20, this is 20,000, this is 1 by 20,000. That should come into your numericals, then only this quantity will be compatible with the matrix multiplication. Okay, so that so here you need to divide it by 20,000, here you need to multiply it by 20,000. That is in fxx inverse, multiply each member by 20,000, and in fxr, multiply each member by divide each member by 20,000. So that has to be done. So if you do that, I have skipped those this thing. Ultimately, you are going to get x1 and x2 as 16.447 and 32 kilonewtons. Okay, because x1, x2 they are forces. So solution process is initial is over. Now you need to go for post processing. So you know that capital Q is simply BRR plus BXX, you know that. But here R, there is an issue. We have one R like this, one R like this, and we have small r like this. This may cause a new R. So you can have R1 and R2. Okay, R1 and R2 will be there. So that's why I have taken VRR into, this is not Q actually, only VRR. Q we will add this to BXX. So this is only VRR. I have taken into 2, that is VR into R1, VR into R2. Okay. So VR into R1 is what you have already done in the previous question. BR into R2 has to be handled a little bit carefully. See, that R1, small r2, sorry, small r2 is in coordinate 4, you know. Here we have small r2. So small r2 is in coordinate 4. Okay, that matrix multiplication has to be, see, you have a VR here, okay. What is BR? BR is the converter or transformer, isn't it? BR is transforming, the original work of BR is transforming global to local. Okay. So uh, matrix coupling is also there. So if you know that BR is size is actually two column, isn't it? Column 3 and column 4. And FRR is also 2 by 2, you know. Okay, it's inverse multiplied by R is also 0 minus 0.05. So when you do this 6 by 2, 2 by 2, 2 by 1 multiplication, the coupling effect will unnecessarily nullify the local forces that you obtain. So that is also can be explained from the principles. I'm just not telling only the principle. The coupling effect will cause nullification. So BR here you have to take only for column 4 only, not for column 3. So this you cannot take. Similarly, this also FRR inverse also has to be taken for coordinate. FRR inverse only taken for coordinate 4 and 4 to avoid the coupling. Okay, this is 1 star to 6 star. So instead of this multiplication, do this multiplication. This multiplied by small r2 alone. So minus 0.005 alone. That is also of coordinate 4. So a 2 by 2 row multiplication, you need to go for only one row multiplication in the second part of the equation. Okay, just one second, I will do that. That is in the second part of multiplication, that is with R2. Okay, in the second, this part of multiplication, you have to be very careful in order to avoid the coupling effect nullification. Okay, one row multiplication. Please note this. Okay, this is important. But the first part multiplication is okay. That is two row multiplication as you have done in the previous problem. Okay, because this is small r inverting. Okay, converted to smaller converted to r force. So there you need to avoid the coupling. So one row multiplication for second part and two row multiplication for first part of BRR. Again, I will explain once again. BRR is BR R1 plus BRR2, where R1 is this one. BRR2 is a consequence of small r. So this one is a two row multiplication as in the previous problem, but this has to be careful. One row multiplication only has to be done in coordinate number 4. That is why I have written BR of 4, FRR inverse of 4, and this small r is modified by two elements 0 minus 0.005 to simply 0.005. So that is a point again to be careful. So there are some points of care whenever you have displacement in small r. Okay, what is the first care? How to take that small r into x. Then once you get that xini, that xini has to be modified by reversing and adding zeros, removing values or adding zeros. So that is care number one. Care number two is in calculating capital Q, that is in BRR multiplication. Second part of BRR2 has to be done only for that coordinates where you have small r. So that is a principle. So in this case, suppose if I add another constraint, another complexity like support A settles by say 10 mm to any direction, 10 or 20 mm. So that 20 mm's value also has to be handled in the similar fashion. So we need a fifth coordinate there. Okay, isn't it? Because that 20 mm of A, you need another coordinate, that is fifth coordinate. So here in this step, you need to second part BRR coordinate 4 and 5's two row multiplication is required there. Okay, there original BR will be 3 row, and that 3 row BR has to be converted to 2 row multiplication. Okay, so 2, that is, I think we got it. So the part one is as usual, as in the previous problem, two, two row, two column, or whatever you say. This R is two row. That's why I told two row, two row, two row. So two row R. You got in the previous problem. Nothing new in this. Second part, I am explaining again. One row. That is this only one row. So pick the 4 FRR from the matrix carefully, because FRR is a 2 by 2 matrix. You have four values. In this, pick which value. You pick this value. This is 4 4. So pick that value and write there. Invert it, and AE will be there. Naturally, AE will come up. That is, AE is 20,000. Apply that 20,000. Then BR also only that 4 column also. Even though BR is 3 and 4, BR is 3 and 4, but don't use that 3. Okay. So that is the multiplication of second part of BRR. So this is the second part multiplication. This is the first part. Anyway, whatever, how many rows you use is different thing, but ultimately you will be getting 6 rows, 1 star to 6 star. That is component of capital Q. So 6 rows you are going to get. Matrix order will be etc. will be very okay, very much okay. Okay. So that to be added, so add them. You get the, this is the BRR part. Now you know that Q is BRR plus BXX. So this part also has to be now added to this BRR. Okay. So this BRR will be added to BXX. So BXX, as you know, we have done it. BXX 2 by 2, 2 row, etc. Nothing modification. So this you get BXX, then add the. So if you add this BXX to the previous BRR, that is this BRR, this is BXX, this is BRR, add them. BR first is minus 10, first element. BXX first element is plus 14, so plus 4 you are going to get as the result. 3 point something, not plus 4 actually. 10 and 14 point something, so that is 3.4177 in the first member. Second member, that is member BC, the force is 14.556, that is also tensile. AB is tensile, BC is tensile. Okay. Then 3 star, that is CD is compressive. 4 star is AD, member AD, that is tensile. 5 star is a diagonal member BD, so that is compressive. Then AC, which we had selected as redundant. You can select AC or BD as redundant, any issue, no issue. You can select for that matter even uh, AB as even redundant. Okay, then everything will be clear. When you take AB as redundant, what is the change? Can you tell me? If I take AB as redundant, can you tell me what is the change here? AB as X1, say for instead of AC selected here. What is going to be the change? What is going to change? Any idea? If you take it like this, I'll explain. Instead of Q, isn't it? This AB, if you take X1, that minus 0.351 L alpha T will be directly taken in X1 coordinate, that is in X in E. So your X in E due to temperature will be converted to minus 0.351 directly and 0. Second, there is nothing. Second is a support. So that is a change. If you select AB as redundant, so you can try that those variations also and check with the answer. So when you do this same problem in different fashions, what is a different fashion? By changing the global coordinate. We have selected AC as the global coordinate x1 and C as the next x2 redundant. So what you can change? You change instead of AC, take AD or BD or AB. So many possibilities are there. Similarly, x2 instead of support C, you select support D. That's also a possibility. Otherwise, you can check x2, sorry, take x2 by removing that pin at A and inserting a roller, or removing 1 degree of freedom, or actually adding a degree of freedom, or removing one redundant from pin support A, hinge support A, and adding x2 there. So all these things are possibilities. If you have time and patience, you can repeat the same problem for different selection of global coordinates, and you will become masters in solving trusses by flexibility method for any given condition. Okay, so I request, if you have time, do this, practice this problem and try to do some other problem by changing the global coordinate. Okay, so with this, okay, you have noticed these values. Please notice the value, and let us finish the discussion. So this problem, I'm repeating, if you know how to do this problem without referring anything, for that you need to know in your mind what is the meaning of capital Q, small q, capital R, small r, capital X, small x. Now, how to decide the number of capital R? How to decide the number of capital X? It is R1, R2, R3, R4. You need X1, X2, X3, etc. You need. If you know that, then you can do any problem. But for that, you should know the principle behind flexibility analysis. What is the principle flexibility analysis? You have already studied in previous semesters and this semester also, SA3 also. The main principle is start from a primary structure. That is, change the structure to primary or change the indeterminate structure into determinate one. That is the primary analysis methodology that you should. And of course, if you are given a determinate structure, then in flexibility, what you can do is you can find out the displacement at various nodes that you can find out because there is no redundant force to solve. And also, you can, if you are given a determinate structure, not only the displacement nodes, you can also calculate the support reactions also. But for support reaction, you need to select those coordinates are support reactions. That is the forces at the support that coordinates has to be selected. So I think be clear on whatever I have just now stated. If you are given a determinate structure, flexibility method can be used to find out the displacements, etc. There is no solution process. There is no inverting in that problem. Suppose you are given a determinate structure, your problem solutions when you write on a paper, you will not see any invert. Matrix inversion you will not see. If you tend to tend to do that, then you are at mistake. Okay. But when you are given an indeterminate structure, of course, inversion is the solution. Okay. So with this holistic idea, I think you can solve any of the problem, and I wish you all the best when you practice these things. Okay. Thank you very much.